The road traffic law has been amended to allow Level 4 automated driving. This will enable driverless vehicles to travel on public roads as long as they meet certain conditions, such as remote monitoring of their operation. Driverless vehicles need to satisfy the same safety requirements as vehicles driven by humans. Uninterrupted remote video monitoring is therefore required. To achieve this, NTT Network Service Systems Laboratories has adapted its cooperative infrastructure platform, which integrates various elemental technologies to realize a robust network for the task of remote monitoring of automated driving. Currently, there are several factors that prevent stable video transmission. For example, buildings may hinder the transmission of radio signals. So, the network quality available to a vehicle is correlated to its location. For example, video may be interrupted in urban areas lined with high-rise buildings or under overhead expressways. Since each mobile carrier designs its network equipment differently, the signal strength at any location varies from carrier to carrier. Focusing on these points, NTT's technology estimates the characteristics of each carrier network available to a vehicle according to its location and radio conditions, and selects optimal networks to achieve uninterrupted video transmission. The technology works as follows. First, it obtains accurate position information from the GNSS antenna mounted on the vehicle. It then calculates the vehicle position a few seconds ahead of time and predicts the qualities of the networks available at that location. Based on this prediction, it selects the optimal network combination and sends video using multipath communication. It repeats this cycle as the vehicle moves on. This combined use of multiple networks ensures stable communication because the vehicle is switched to a higher quality network before it enters an area with low predicted communication quality. Let's look at the results of an experiment that demonstrated this technology. First, let's consider the case where NTT's technology is not used. When the vehicle was traveling in a low network quality area, the video stream was disrupted and then interrupted. Now, NTT's technology is used at the same location. As you see, the technology prevented any video interruption. At this other location, the technology also maintained normal video transmission. This graph shows the measured transmission throughput of the monitoring video when this technology was not used. The networks of carriers A and B were available in this area, but the vehicle used only B's network. When it came to a low throughput area, the video was interrupted. In contrast, NTT's technology predicted the network quality of carriers A and B a few seconds ahead of time. The red curve shows the throughput of A's network, and the blue curve that of B's. The technology predicted the quality degradation in B's network and switched to A's network in advance, thus avoiding video interruption. It maintained the quality of the monitoring video by making multiple networks complement each other. Going forward, we will deepen our study to achieve social implementation in cooperation with operating companies. And we will expand the application of this technology to smart agriculture, smart cities, and other areas to realize highly reliable networks that support social infrastructures.